4 p.m. Eastern Standard Time, and now we will commence. Hello and welcome to this AI4 Cybersecurity webinar. My name is Michael Weiss. I do content for our AI4 Cybersecurity conference, which is here in New York on April 29th and 30th. And so today, we have a very exciting webinar, and we've split it into two sessions. So session one, which will be the next 30 minutes, is with Chip and Richard here, is going to be a conversation around how AI is changing identity authentication. And they're also going to cover the privacy concerns which are abundant related to that change. And then session two will be with a fellow named Philip, who's a PhD researcher at NYU. And Philip had a project that went pretty viral not too long ago because he was able to use machine learning to essentially create these master prints, these fake fingerprints, which can unlock biometric fingerprint sensors. So now, without any further ado, I'm going to kick it over to Chip and Richard to do their self-introductions. And remember, I need a fun fact from each of you.
Go ahead, Rick. You can go first.
So, hey, I'm Rick Borden. I'm a lawyer. You actually get to listen to a lawyer here. I've been doing this stuff a long time. Things that might be useful to know. I was the chief technology lawyer at the Hartford for about 8.5 years. I was the cybersecurity lawyer at Bank of America. I also supported the CIOs that make up Merrill Lynch there. I was the chief privacy officer, chief technology, and cybersecurity lawyer at the Depository Trust as well. Now I'm in private practice. Fun fact about me, I guess fun fact is I play guitar, learned it recently, not all that well, but I have a lot of fun at home.
That's good. Yeah, I'm Chip Block. I'm Vice President of Converged Security Solutions, which includes Evolver. That's because we recently were acquired, which is something that I've been through multiple times now. I've been in the technology business for a very long time, going back to the point when we make our own processing boards, and my first computer was a TRS-80 in 1977, Model 1, and have been involved in both the cyber side and the development side for a very long time. In 2003, interesting, got a R&D 100 award, 100 most significant products in the world, for developing the first scientific application to run on a handheld computer. And I've been involved in the cyber world now for quite a while. We here at Converged Security Solutions, we're in the cyber operations business. We monitor and run cyber operations for large financial, government, healthcare companies. One fun fact about me is I at one point tried to be a tennis pro, and since none of you have heard of me, you can see that didn't go so well. But that's a little bit about me. Cool,
thanks guys. All right, jump in. So let's start with some definitions. What is the automated processing of identification data?
So I think a good place to start is an example. And I'm going to use an example of a building and where the world is changing and where AI and machine learning kind of really come into play here. Right now, most of us, when we think of identification, we think of discrete identification. What I mean by that is you have some form of identification, whether it be a driver's license, whether it be your social security number. It is a thing. It says, this is my discrete identification. You either give it to somebody, your username and password, or you have, it's kind of discrete. However, we're moving into the world of derived identification. And let's take as a building that I monitor a building every day, and I monitor who comes in, when they come in, how they come in, and then I pick up a piece of information, maybe their name, I pick what they do, and from that I'm able to derive who that person is. That person didn't give me their identification. I derived it from a learning activity, and now I have the identification of who that person is. I could associate it with their face. So that's an example of where we're moving away from just a discrete identified world where I could say, this is me, to a world where we're able to derive who people are and information about them. And that is probably the area where in the AI and machine learning world, where we can use learning techniques and models to actually create that without any pre-structured information into the model in general. That's an example of kind of where we're going in the identification space.
Well, and so to play off of that and talk about how that relates to privacy. So let's say, you know, I walk into a building and they derive my identity. One of two things is going on. Either I work in that building or I don't. If I work in the building, then it connects into the HR systems and other things to make sure that I'm authorized to enter and where I can go within the building. So that actually connects in and connects to personal information that is about the person or about me. If I don't, the information's going out, they're going out and getting information somewhere else and connecting that personal information to me and storing it on the building network somehow. So there is now personal information about me that's being stored there. Now that means that whoever's running that now has personally identifiable information through biometrics and other information about me. Well, there are laws on this stuff and more being passed every day, and that can create a lot of issues if you're not doing this correctly.
It's interesting. I think already we got some good questions. Somebody asked difference between derived identity and multi-factor authentication. One of the things that we're talking about here is don't assume that you are, when this derived information about you is being created, that you are giving permission for that to happen, right? But this is a touchy subject because I could make a case that if you're in my building, I have the authority to know who's there, okay? But you didn't give, there was no signing of papers or authorization that said that in the first place, right? I created that information, right?
Right. So, right, but so here, just to tie it back to the derived versus multi-factor, these can go together. They're not necessarily separate. So what might happen is, let's say you're signing into, let's say it's not a building, let's say you're signing into something and the webcam's on, and instead of sending you a message on you know, SMS, which is not very secure, it instead takes a look at your face, or your phone looks at your face and says, okay, that I'm going to use the information that I've got and connect it to other information, which could be through multi-factor, or the multi-factor could be looking at your face and going out and comparing it to a whole bunch of different things to derive that your identity is yours, and that is even more secure. So derived identity can connect to other authentication methods.
Right. And by the way, that's an interesting point, because we're talking about cybersecurity. Last week I spoke at a large conference and it was all about identity, and one of the things we talked about was digital identity, being able to do digital proofing of things. Now this can work in several different ways, which is, can I identify patterns of usage and capabilities in order to derive an identity both from a positive, this is who I think it is, or negative, this could be a threat or an attack vector, right? Well, we keep running into this issue of, if I do that, what can I do or not do with that information? If I derived your identity because you came to my website, I determined your location, your actions, your capability. By the way, just for everybody to understand, we're not talking about technology that's way out in the future. We can do this today. We're not out into Star Wars land. This is stuff that is available today and possible in order to derive a digital identity of a person. A major credit card
it's being used.
It's being used today. So we've created this world where I'm going to derive who somebody is. Now I'm going to take actions against that, right? I'm going to shut off what you can do, what you can't do, or things of that sort. That could be on a positive from a cyber perspective. It also could be used as a negative in order to spoof identities, create false premises of people, things of that sort.
Yeah, well, and this is where you start to get into some of the legal areas. So there are some laws out there now, Illinois being one of them, on the use of biometrics and having to consent in writing to how biometric information will be used, and also it has to be disclosed very, very clearly, including on a website, how that's going to be used. Now, which is a really interesting thing, because as you know, cyber is adaptive. That may be very difficult to get that clear consent and to give that disclosure, because things may be changing quickly on how that happens, because the attackers are going to look for the holes. So you've got the laws on one side, and there are more being passed. New York is looking at something, you know, some other states, and there are real damages around this. I mean, these are what they call statutory damages. There's going to be a lot of lawsuits. There are already in Illinois. So the use of this information can be very powerful, but it has to be done, as Chip said, correctly. And that is becoming much more difficult. So you have to be working with people who understand the regulatory frameworks, all of the stuff that's going on, and the technology. It's got to be this combination.
Yeah, that's good, because I think it brings up a point because I think on this call, we've got a number of folks who are probably developing new applications and new products. And let me tell you where this dramatically changes how we kind of do things now and how you go forward. And it may actually change the structure of companies. Right now, we kind of live in a deterministic development world. We assume when you build something that there's the magic checklist that I could go through and say, okay, tell me what the code looks like, how do I protect it, what's going in, what's coming out, and I do this evaluation. In an AI world, of course, that doesn't exist. We are creating outcome-based applications and products. Well, you don't know what the outcomes are until the actual model expands and derives itself. So if I don't know that, how, and I'm going to ask you, Rick, from a legal perspective, how would I be able to say, I don't know what my outcome is going to be, because I don't know what the learned behavior will be, and I don't know what people will use it. I don't know how they will use it. How does somebody put a product plan around that when this is going to be very, because again, I can't have a checklist like a NIST 800-53 that I just go through and check off and say I'm good, because there's no way of being able to do that. I don't know what the outcome will be.
Yeah, I mean, that's a great question. So there's a concept called privacy by design. You also have security by design, and there's security regulations that are, you know, laws that are being passed as well. But privacy by design, it came out of Canada. It's used with GDPR. You're going to really need to use it for California and some of the other laws that are coming out. And what that means is you have to start really early in the process, and you have to be designing. So if the outcome of automated processing, and there are restrictions on automated processing and what you can do with that, what legal effect it can have in places, you have to have a process around it. You have to have it built into what you're doing with that information and the decisions that are being made as part of the very basics of what it is that you're doing. So you have to have all of this built into the, you know, the design, and that is different. That's really fundamentally different than what the processes have been before, especially when you're dealing with AI.
Okay. So I would go back to a question we did get earlier, which is somebody said, can machine learning techniques solve our computer security problems and put an end to the cat and mouse between attackers and defenders? I'm sorry, no. I live in this world. I live in this world all the time, and this is not a solvable problem. This is a risk problem. It will be there forever. We are, on one hand, we will create new solutions to address problems. Right now, when you think of AI and cybersecurity, it has primarily been looked at for anomaly detection, right? Which is, how do I create a model of the current activities within my environment? And that's a rapidly maturing capability, particularly on the machine learning. We haven't quite got as much on the AI side, as much machine learning around anomaly detection. I think we're moving into a really different world now, and I think this identification that we talked about is a really good area to talk about that, because if I can create both the ability to identify or create the ability to falsify identifications. Identifications is the key to pretty much all cybersecurity, right? If I know who's there and I know they're good, they can do X. If they know they're bad, they can't do X. Well, if that is going to be a highly fluid and dynamic environment, which AI I think is going to create, it's going to make this problem. I'm not going to say it's going to get better or worse. It's just not going away. This isn't. There is no magic bullet. AI will make it different. I think it will accelerate speed times. I think almost everything in the cyber world is measured in timing, and I think there's, what used to be days is now seconds and soon nanoseconds of the actions and reactions of where we live in our world. So I think that's kind of where this, I wanted to address that question. I've got a question for you, Rick, kind of related again on the legal side. Let's talk about liabilities of companies and maybe third party. If you're dealing with a company that's providing you an AI solution, and let's just say you're using with a company using an AI solution to provide you identifications. What is some of the things that are there that they have to address?
Yeah, so that's a big question, and it goes along kind of with a question that we got about how does derived identity work with GDPR. So if you're using identity and you're making decisions that could affect somebody based on that, or you're processing their personal data, to use an EU term, then you have to have legitimacy. So in the EU, under GDPR, you have to have either consent or a legitimate interest to use that information, just to make it simple. Also, if you're using automated processing, it can't have a negative legal effect on them unless there's a human intervention somewhere. So you can't have it automatically have a negative legal effect on them. Now, and that's where you're not quite seeing California go there yet, maybe, but you will be seeing probably Washington State, maybe Massachusetts go there. So this is coming to the US. What it means in effect is that you have to be very careful in how you collect this information, store the information. You have to be thinking of the legal aspects of collection, storage, transmission, every piece of this, use, and then what you're doing with the results. And at each of those places, you've got, and I should add processing, each of those places, there are legal decisions that are being made that, if not done correctly, could put you far out of compliance and put you in the middle of class action lawsuits, attorney general investigations, FTC investigations, GDPR, EU regulator investigations, all at the same time even. So we're moving into a very difficult environment right now.
So one of the things as we go to desires like to bring up is, on these type of things, is where actually could new technologies or new things be? And I will give one to the crowd for those who are building AI solutions out there. One of them has to do, and it goes directly with what Rick was talking about. One of them is the use of AI for time constraints of data, right? This is one of the things that we've talked a lot about on the cyber side and related to the identity side, is to be able to say, okay, I'm going to give somebody access to certain functions, processes, data, capabilities for some limited period of time, and be able to derive what that should be, how that should be, and how that actions. And where that gets back to our example of the building, I don't necessarily know who those people are. We all know how to do that right now. If you gave me a list of people and you said that these people can have access to this information. But if I'm in a derived identity world, I'm going back to my building, and you mentioned like a bank. If I said, I'm going to give the following people who enter this building derived access, or I mean, I shouldn't say derived identities, access to the following functions on a 5-day period. I don't know who they are until they get here. So when they get here on Monday, they have access till Friday. Those types of being able to create solutions that can learn and say, hey, this is there. I think that also could go to a legal side, because you could, it is that long-term storage thing that usually will get everybody in trouble. You could say, hey, I created this. Now, there's a downside to that, because if those people were doing something illegal or they're doing something they shouldn't do, and you wiped out all that information the following week when the police showed up, that could be an issue. So you kind of have that push and pull before what can I do with it and what can't I do with it.
Yeah, and you have to keep it for as long as you need to from a legal standpoint. But I'd like to bring up something good that can come from some of this stuff as well. So imagine that there's a building and there's a fire or an earthquake, and first responders come, and they really need to know how many people were in the building, where were they, have we accounted for everybody? Well, if you're in a building where it's tracking your identity through biometrics, cameras, whatever, all through the building, and it knows that it's you that was on the 6th floor. Well, when something like that happens, you can much more effectively, help the first responders to know, yes, we've gotten everybody out, or no, Chip is still in the building and we need to go find him, and we're pretty certain he was on the 15th floor, by this room when this occurred. So and that's just one example of things that are good and legitimate and things that we would want to have. We just need to make sure that as we're doing it, that we're using it for the intended purposes, that we're able to explain what those are, that we make this clear, and that's the balance. So this is all balance. It's balance of risk. It's balance of, but it's really being very thoughtful and building this in at the beginning.
And by the way, related to that, very similar on the cybersecurity side, one of the things we don't do, but the easiest cybersecurity approach right now would be, number one, I'm not going to let you log into your computer at your desk if you're not in the building, right? By the way, so I could derive who's in the building. I could derive where they are. I could see that by the way, I could also derive they shouldn't be in the server room. Not that that would ever happen. Somebody would randomly walk into a server room, but it obviously happens a lot. So that is one of the other areas. I think the other part that gets interesting from a kind of an interesting perspective will be the detection of AI. We've got a couple of minutes, but I want to get into, it's called the AI salting side, which is the ability of people to actually manipulate the models, manipulate the capabilities. We're about to hear from a biometric person who's done some brilliant work in this area. One of the things in the model world is if the model is salted wrong in the first place, then that's the way it's going to behave. And if it was unintentionally or intentionally falsified to begin with, you're going to be stuck with that information. Now, in the legal perspective, I'm deriving wrong information. I'm providing the wrong information for the wrong action, for the wrong capability. And from a cyber perspective, how do I defend myself?
Yeah, so an example is there are articles about being able to tell about somebody's mental health based on voice. So an employer makes a decision not to hire somebody because they use an algorithm from an through an interview, and they decide that the person, has some mental illness or some, something that they don't like. And the algorithm was either wrong or was, the trained algorithm was manipulated. And you take a legal effect based on that, right? You don't hire the person, or you fire somebody or something like that, right? Then you could be in real trouble. You could get a big lawsuit and have significant liability for that. So, the manipulation of these things could be very, very detrimental and at scale. That's part of the problem. When it happens, it'll happen in large ways, and companies can go out of business just from that.
So,
you guys are crushing it. So we're getting to end here, but you just got a couple more questions. So why don't you field these, and then we'll transition to Philip.
So here's the questions. One of the questions is how is biometrics a derived identity and not discrete? If a biometric would be discrete if I already knew who you were and I compared your fingerprint, as an example, to a file that said that is Chip Block. A derived identity was I don't have any. What I'm basically doing is I'm figuring out, say, facial recognition, that you are showing up regularly at a certain times, or I'm using that. I pick up a fingerprint at the counter or whatever, and I'm going to combine that with other information and determine who you are without any of the discrete value to start with, right? So that's just somewhat of, so as I understand, that's the difference between derived. Derived is no necessarily provided capability up front that I'm going to figure that out. So that's one question.
Which, by the way, might be better from a privacy standpoint because we keep less information on file about you.
Right.
So since we're doing it, that's data minimization is required. So deriving identity from other sources might be better from a privacy standpoint in many ways.
So, the other question, we only have a few minutes. I would love the state of control environments right now is a great question, but that I don't think we're going to be able to cover in a couple minutes. It's a really good question. Maybe, Michael, you want to have another one. I could talk on state of control environments right now for quite a while. We may want to get that one another time. You're on mute. Hey, Michael, I think you're on mute. So.
I said, give us 60 seconds, Chip. This one's for you, Stephen.
Okay. So you talk about the whole structure about state of control. So the idea of being able to go in and apply some kind of standardized control set that I'm going to be able to measure somebody and then be able to then determine that that they are that I'm going to be able to stop the black hacking structure is, I don't want to say silly, but we've gone to the point that there's no way that I can come up with this list of things I need to do, these list of standardized controls that I'm going to be able to put in place. We are in a dynamic world. What we need is the idea of dynamic controls or derived, similar to what we're just talking about. I almost need a capability where I need an AI control environment to combat AI attacks. That seems like a redundant capability, but that's almost where we are. To come up with a standardized state, a control state at this point, I think is, I don't want to say silly, but borderline silly.
And we'll end it right there at borderline silly. Thank you, Stephen. And there's one more question, but we're gonna have to get to it later. We're getting a couple more. Okay, so now thank you both, Chip, Rick, you guys crushed it. You can say hi to Philip digitally here.
Hello.
Hello. Is my
Hey, Philip.
All right.
Hello. There we go.
Perfect. And so now we are going to say bid adieu to Chip and Rick. I welcome you guys to stick around. And then I am going to go ahead and briefly introduce our next presenter, who happens to be at Ai4 Cybersecurity headquarters here in Brooklyn Heights, New York. So Philip, he is a researcher at NYU. and he's done some really cool work related to this idea of the master fingerprint, which is essentially, well, I'm going to let Philip do it. Philip, take it away.
Okay. Hello. Let me get my screen going. And there we go. Okay. Can everybody hear me? Is there a way to know?
They do not know, but they can.
Yeah. Okay. So I'm going to be presenting on this work that I did with some of my colleagues called the master fingerprint, and around some of the AI and the implications that I think are interesting around that. So just a little bit more about myself. I'm a PhD candidate here at NYU in New York. I've got about with my main focus being artificial intelligence. So within artificial intelligence, the area that I find most interesting is this area between data and machine learning and creative agents. So creative agents, there's been a lot of work around that, and they use different, mostly optimization algorithms, trying to design things, which can be as varied from creative things like a video game, or to more practical things like design for a wing of an airplane, or to fingerprints, which is in this case. And I believe that by adding data of human examples into the mix, these algorithms can be informed and do much better for both positive purposes and, as you'll see here, malicious purposes. So at the beginning, I want us to talk about some of the advances in AI over the last few years that we've been seeing. So here in front of you is an image of of faces that came out from a model that NVIDIA put out about a few months ago. And all of these faces are completely new faces that have been generated. They're not pictures or anything like that. And this is a huge leap. Even a few years ago, the best that people could do were very horrifying looking nightmare-esque faces. And it's able to learn all of this just from data and examples. Another example, this is just from like a month ago from a research team called OpenAI, and this is a big advance in text generation. So at the top you see there's a human prompt, and this is just a one sentence prompt, and that's provided to the network, and it generates a whole long story. I've included just the beginning of it in the slide. And this is very impressive in the whole consistency of the story. If you read through the whole story, there'll be details that will be conflicting, but overall, it's a very well constructed story, trained on about 40 gigabytes of internet data and on a lot of cloud computing resources. And the final example is from DeepMind on playing StarCraft. StarCraft is something that was believed to be like kind of the last really big, difficult game. And now people are kind of looking for the next game to beat, but they just came out with an agent that is able to play at the top human level and compete against the best StarCraft players in the world. And this is a difficult challenge because they're playing only by watching the screen, and they have to manage their economy and resources in order to build an army, which they're also in real time managing to attack and defeat the enemy. So there's a lot of real world like applications. So on the whole, AI in the last few years, specifically machine learning, has made a huge amount of progress, and it can do a lot of things that are human-like. And if you're not aware of what's going on, it can take you by surprise because you would see something and you would be sure that a human had created it or taken a live photo of it, just because it was unreasonable just a few years ago to assume that a computer was doing those things. So computers have gotten a lot better at imitating humans. On the other side of that, if you look in more detail at, like here, these are more examples of those images that I showed on the first slide. If you start to study these, you can actually tell the difference between real pictures and these generated ones. There's actually a game online where you can see how good you can be at this. And you realize there's some common patterns. Like if you watch the outline of the hair And the backgrounds are normally blurry. There's a hard line here. And then also looking at the eyes, they're not always facing the same way, or there's a difference in size. Another example, which comes from some of my work, is these systems can do amazing things like learn to play StarCraft if you put them at the right scale, but they're also very brittle when you change the situation just a little bit from what they were expecting. They don't have the same reasoning power that we expect when we see them do amazing things like compete at a professional video game player. So this is a very simple game where you have mushrooms that you have to collect. And the more mushrooms you collect before the end of the game, the more points you get. But the catch is that if you collect the mushrooms once they're fully grown, they're worth many more points than they are when they're right at the beginning. And you can see while it's training, it learns pretty quickly to collect mushrooms. But then it gets so good at collecting them that it can't get a high score because it doesn't figure out that it needs to wait for the mushrooms to grow. So it collects them very quickly, and its score drops off, and it can never figure out why it's getting a worse score now while it's getting a reward more often. So I just put that out there to point out that these agents are very human-like. They're getting a lot better at things, but it's only in one dimension. Whatever dimension they're optimized for, they can be very human-like. But then if you look at, it's like if you looked at like a cardboard cutout of a person. You see the person, but you walk around the back, it's just a flat cardboard cutout. And I just wanted to lead into my talk with kind of this background because the work that we're going to look at is what happens, the vulnerability you can get when you look at a system that hasn't been designed with this sort of AI in mind. And there are a lot of vulnerabilities out there, but it's not an insurmountable task to defend against these because there's a lot of brittleness in how they actually work. So I believe, and in the future work that me and my colleagues are working on, that these sort of things can be detected and defended against when it comes to malicious use cases. So the work that I'll be talking about and mainly presenting here is my work and my colleagues' work on deep master prints. So I worked with myself and some professors and students from New York University and Michigan State University. This work, we designed a fingerprint that was able to match in a test situation 23% of the people. So in like a virtual environment, you could pick up 23% of the phones and you could unlock them. And this actually, it picked up a lot of press and we got an award for it, which we always enjoy. So what is a master print? So getting into this, in the most general sense, a master print is a fingerprint that is similar to a lot of other people's fingerprints. It can be real. Like if you look at a real person's fingerprint, they might technically have a master print, so like my fingerprint, if it happens to be like a lot of other people, it could be like a natural master print, but it would have, from everything we saw, a natural master print means that it has a chance of unlocking somebody's phone slightly more than a regular fingerprint. Not much of a difference, not like 23%, it'd be like 0.2% or something. So one of my professors noted that these master prints probably exist. There was some previous work that showed that they did exist, and we hypothesized that if you could synthetically generate images that were these master prints, that you could actually make this attack happen. So into a little bit more background about how this works, the closest thing that I think to it is like a dictionary attack. So in passwords, if you have somebody's password and you're trying to guess the password and you have a computer, you can try to go through all the possible combinations of letters and numbers and characters. And if their password's very long at all, it'll take like thousands of years to solve the problem. But if the person is using very common words and patterns, you don't have to try every possibility. So this is very common in password cracking, is that there'll be a very large database of very common words and patterns that are used in passwords, and then you try all of the possibilities of just these common words. And it won't work for everybody, but you have a high % chance of unlocking somebody's password in maybe an hour on your laptop, which is much more reasonable. And what we're doing with machine learning is trying to do the same thing, except for with biometrics, which I don't believe it's been done before. So we can design, or the computer can design a biometric or a fake fingerprint that can unlock, that has a lot of common patterns from real fingerprints, so that it can try to unlock the real fingerprint. Do you have the questions?
If someone asks, how are real prints data selected when training for master prints?
Yeah, so I'll get into how we do this in the coming slides. Yeah, so to go a little bit more into the background, it's this type of attack is the presentation attack, which means that we create a fake spoof and we apply it to the system. You don't need any sort of, you don't need to be inside the system or hack the system. You can just apply it straight to the sensor. Another thing that makes this possible is we focused specifically on smartphones. A smartphone fingerprint reader is typically very small, so it doesn't actually scan your full fingerprint. So what this means is if I registered my fingerprint on the iPhone, I would try multiple versions, and in order to unlock it, I only have to match part of one of those. So if I scan these 4 parts of my fingerprint, then to unlock it, only one of these 4 parts has to be presented to match. And a small part of your fingerprint isn't nearly as unique as your entire fingerprint. So in this, we tried to create, our master print is just a partial fingerprint. So it's like, what is the most common part of everybody's fingerprint that would be registered in many smartphone systems. So this is the actual algorithm, and I'll break it down in small parts so it shouldn't be too bad. So first, we need to generate a fingerprint, and we need to see how good is it as a master print. So I'm going to go into how we generate fingerprints. This is using a very similar algorithm to what I showed at the beginning with the algorithm that could generate faces. Except for in this case, our data is fingerprints instead of faces. So we use an algorithm called Generative Adversarial Networks. I won't go into how that works, but what it does is we have a code, like a small code of just numbers, and it converts that into an image. And what it does is it learns over time that you give it lots of random codes, and it's penalized if the image doesn't look like the original data. And over time, it learns to produce for any code an image that looks like the original data. And what this now allows us to do is we have something that gives us a bunch of different, like potentially millions of different fingerprints, both real and between the spaces that exist in reality. And then we can just search for, we just need to find the right code that would give us the fingerprint that is our master print. So next, we need to know how good of a master print our fingerprint is. So here we can use just an off-the-shelf matching system. So if you had like an office and you wanted your employees to use their fingerprint to get into at the entrance of your office, you could buy one of these systems. And it would have a database of all your employees, and as soon as they put their fingerprint, it would scan the database, see if one of the people in the database matches, would unlock the door. So we tested several different one of these systems, Verifinger, Innovatrix, and a government like benchmark test. And the way this works is we have a data set of identities, and we present our fingerprint to the system. And in the example image here, you can see you have 3 identities, and each one is broken into several partial fingerprints. And as long as one of the partial fingerprints matches, then that identity matches, and you get a score. So in this example, our fake fingerprint got a score of 2 out of 3. And so now we can score our fingerprints. We can create a fingerprint and we can score how good of a master print it is. And now we just need to find the fingerprint that gets the highest score. So for that, we use an optimization algorithm, which is based off of evolution, similar to the idea of natural selection or breeding, where we start out with a bunch of random codes. We create the fingerprints, we get their scores, and then we take the best ones and we move them on to the next. They get to live to go to the next generation, and we mix the codes from the ones that survived, kind of with the idea of breeding, in order to create a new generation of codes. And we repeat this process until we get a code that has the best score.
So somebody asked, does this attack work only against optical sensors, or does it work against capacitive sensors also? How about ultrasonic sensors?
Yeah, so this attack isn't specific to how the fingerprint sensor works. The main constraint that we're taking advantages of is the size of the fingerprint. So we in our tests, we only tested everything at the image level. We didn't make a real world example. But Aaron Ross, who's on his lab in Michigan State, works a lot with creating fake fingerprints, and they're able to create fake fingerprints that will be read by capacitive sensors, by optical, by ultrasonic. But there's still ongoing work to see how well we can actually create these images in real life and get them to work. So that's future work. But the main difference would be maybe like an ultrasonic sensor that's behind the screen could potentially scan a larger part of your fingerprint, which would make it, that would be more unique and would be less susceptible to this type of attack. Okay, so that's latent variable evolution. That's how we can create these master prints. Now let's look at the results a little bit more. So we use a data set which was published from a Chinese research group. And on the right there, you have some example images from the data set. These are capacitive images, so they're scanned from a capacitive sensor. We had 720 unique individuals where we kept the right thumb for each one of those. Of each of those, we can then break the full fingerprint down into many small partial fingerprints. So what you see on the right is a few partial fingerprints that we pulled from the real data. And underneath that are some generated samples. So you see that we're able to train a model that can produce images that are very similar to the real looking ones.
So somebody asked, actually, Vishran, let's save this one till the end. Yeah, we'll save this one till the end. We'll come back to it.
Okay. So now these are what the optimized fingerprints look like. You'll see they look a little bit different than our randomly generated ones, but we'll get to that later. And what we do here is we optimize for different false match rates. Now the false match rate is how often you would expect your system to allow an incorrect person through, that it would find an identity incorrectly. And you optimize your system for different false match rates, as I'm sure many of you know, so that a very low false match rate is very secure, but is very inconvenient for users because they might be incorrectly rejected and they have to retry several times. Versus the higher false match rate is more convenient but less secure. So at the top, you'll see the false match rate that the system is optimized for. That means our fingerprint should have only matched, in this case, 0.01% of the time, and it was getting 1.1% of the applicants. Here, 0.1% of people should be falsely accepted, and we got the 22.5% that we reported earlier. And if you went up to a 1% false match rate, we were able to get over 3/4 of the people in our test situation. So we were able to do much better than what these systems are optimized for, and we highlight the 0.1% false match rate because that was more similar to some of the systems in the wild at the time of our research paper. One thing I want to point out, going back to where I started with this presentation, is that if you look at these fingerprints, these are the three that we show in the paper that are optimized, they have some properties of fingerprints. You can see around the outside edges that they're real fingerprints. But there's also a lot of noise and other garbage in there that a human looking at this would wonder what was going on and maybe have the person retry. So these AI systems are taking advantage of the fact that that these fingerprint matching systems are expecting real fingerprints and not synthetic fingerprints. So it's not enforcing kind of overall global structures that it would expect to see in a real fingerprint. So I mean, if you added those enforcements, then our system could probably keep trying to beat them, but it would probably have an overall less of success. One thing we also originally tried is just with random noise. So if instead of something that looks like a fingerprint, you can create a noise pattern, kind of like the static on your screen, that can get some success in one system, but when you try it on another system, it doesn't generalize at all. By having it look like a fingerprint, we're able to optimize for one system, like a data set in Verifinger, and then test it on another matching system like Innovatrix, and we're still able to get success at unlocking. Not as high as the system we optimized for, but there is a decent level of generalization, which is the problem when an attacker can take an off-the-shelf system and a random data set and design something that then can be used on systems that they never even had access to. So I just want to conclude that the overarching point that I wanted to give with this talk is that AI and machine learning, they're advancing a lot in how they can imitate people, how they can appear like people, and in doing tasks that we thought only people could do. But they're still very brittle when compared to people and focused on single objectives. So if careful work in any space is given to what the AI could do when it's trying to impersonate a person and what the differences are between impersonating AI and a real person, I believe, I mean, it's nothing you'll ever solve permanently, but it'll be a back and forth game that you can keep up with in identifying the differences between the person and the AI who's trying to be used maliciously. And in our own future work, we plan to try to show this with the master prints to be able to show that you can identify these fake ones. So thank you.
Cool. Thank you, Philip. Fascinating work. If everyone could please clap at your desk, it's honor system. All right, so we have a few questions before we call it. So Restaurant, we'll do yours first. So here, let me do my video so I'm not a random voice. Okie dokie. So Restaurant asks, what would be your opinion on the use of fingerprints to log into banking apps and other apps which should be secure? Because it seems as the phone is recording only a small part of the finger anyway, is it much easier to spoof?
So I mean, already my focus is more on the algorithms and biometric side, so I just wanted to pre-qualify any of this stuff, that like, what is the appropriate security level to implement in systems isn't my expertise level. But that has to do with, I mean, before they had fingerprint systems to unlock people's phones, people were left to use passwords, which they were using bad passwords. So I mean, I think it's still a better step than where things were before everybody had Touch ID or other fingerprint sensors on their phones. Yeah, it's up to the systems to get more secure, and maybe if a phone doesn't have a very secure biometric setup, then they can also require a password or a PIN or something.
Fair enough. All right, so then Stephen asks, I suspect an implication from your info is that this can also be applied towards creating master iris images.
Yeah, so the approach we're using in many ways isn't specific to fingerprints. So we are investigating things like faces and irises. The thing is, a big key to the success that we had here was the small fingerprint aspect. But it's reasonable to expect that other biometric systems have taken other shortcuts in order to be either more robust or more convenient. So like irises, they allow a certain amount of occlusion based off of how high your eyelids are or the angle of your camera. But this isn't something that we've shown yet. Yeah, theoretically, if you can find a way that maybe some of these other biometrics are less secure than we thought, or are like less unique than the full theoretical version, then we could take advantage of it in the exact same way. And even if you don't find that, you could probably still create a master iris, but it probably wouldn't be as successful. But once again, this is work that we haven't done yet, so I can't say that for sure.
Cool. All right, then there's one more question here. We'll finish with this last one. Is there any way to know how unique a fingerprint is? For example, what are the chances my fingerprint can be spoofed? Like ease of spoofing.
I mean, you could design your own test. There's not an easy way that I can think of, where you put yourself in a system and then you test it against a large data set of other people's fingerprints. But in general, I don't know how worried you would be about that. Like if you wanted to reduce the ease of spoofing on your own like smartphone, when you register your smartphone, your fingerprint, always use the exact same part of your fingerprint. Then in order for somebody to match, they would have to match that exact same part instead of a bunch of different parts. But in general, even for like some natural fingerprints that are, I would say, more spoofable or also more easy to unlock other people's systems, it's still very low compared to like a synthetic one.
Great. Well, thank you very much for joining us here, and thank you to everyone who tuned in for today's webinar. If you'd like to check out our conference at the end of April here in New York, you can come to AI4 Cybersecurity. Just, I think, type it into Google and you'll probably find your way. And thank you to Chip and Rick as well for a great first session. Goodbye, everybody, and good night.
Yes.